Okay, so thank you very much for coming. You may have heard the talk last Tuesday, which was a public talk at Fermilab by the g-2 collaboration, which gave the results of the final analysis of this very important experiment, which is called the Muon g-2 experiment. So the measurement of this g-2 of the muon, or the anomalous magnetic moment of the muon, it's a landmark measurement, and it's a great achievement in the field of elementary particle physics, and it has been dominating the landscape of standard model physics as well as beyond the standard model physics now for over 15 or 20 years, partly because of a discrepancy between the measured value and what we call the standard model value. So the New York Times actually reported after this, saying that it is still not clear whether there is a discrepancy or not, while other newspapers have said that there is agreement between the two. So one of the aims of this talk is, of course, part of community service, is to inform the community as to why this experiment is so important, and that's what I plan to do now. The first run of this experiment announced its results on April 7th of 2021, 4 years ago, which was in the middle of the COVID season. In fact, it was a second wave. And soon after that, Professor Arunan in chemistry had asked me to give a talk online, obviously. And at that time, since we were all trapped at home, there was no way in which I could prepare slides, but I decided that I should give that talk. And it was a talk that was based on just my notes, and I found my own handwritten notes from that era. But after that, since I have given this talk many times after the run one, I was able to find my slides and I was able to update them to the extent possible. But today we'll also have Leo, who will tell us a little bit more about some of the details that may be missing. So since this is a very general audience, I should start off by also so a brief introduction as to what is the muon. The muon is a very heavy cousin of the electron. It is about 210 times as heavy as the electron. There's a rather small slide which gives many of the properties of the muon. But in the next slide, I'm going to tell you a bit more about what it is. The muon is an unstable particle because it also participates in the weak interactions. If there were no weak interactions in the universe, it would also be stable, and it would be just like an electron, except that its mass is different. So the parameter that distinguishes between the electron and the muon is the mass. And the measurement of the muon g-2 is particularly important because it's possible to achieve this for a variety of reasons that we will discuss over here. And its lifetime is sufficiently long because in its rest frame, it actually lives for about 2 microseconds, which makes it a very long-lived particle. And as we will see in the experimental apparatus, it has very high relativistic motion. So actually its lifetime increases to over 60 microseconds in the laboratory frame, which allows us to do many more experiments. So obviously, since it's like an electron, it interacts electromagnetically. Therefore, the properties associated with a charged particle are, of course, its electric charge and also its magnetic properties. And what would be of interest to us here is what is known as the anomalous magnetic moment. If it was not anomalous, there would be a number which is the gyromagnetic ratio, which would be equal to 2. So the deviations from this 2 is what we call anomalous magnetic moment. So in fact, it's the classical Dirac theory which predicts this gyromagnetic ratio to be 2. And everything that we will discuss in this talk and in this experiment is what are the deviations from this value of 2 because of the presence of virtual interactions in the vacuum, which is a feature of quantum field theory. So stated differently, so you have the muon over here which interacts, say, with a static electromagnetic field over here, and this vertex here is what gives the number 2, and in the absence of any loops, it would just be 2. But because of the presence of loops like this, where you may produce a virtual photon which interacts with other particles in the vacuum, there's a correction to this value. Now you have to imagine the muon to be a particle. It's a spin-half particle. You have to imagine that it's like a magnet that has got a direction of magnetization like this. And when it is immersed in a magnetic field like this, it is going to precess because that's what magnets do. In our experimental configuration, actually, this muon polarization will be lying in the xy plane, whereas we will set it up in such a way that the magnetic field actually points in the z direction. That's a kind of an optimal configuration. So you have the maximum possible precession, which is Larmor precession of this magnet in this magnetic field. So the early experiments for the muon were done in CERN in the 1960s, which had a large uncertainty. And the new experiment is a Fermilab muon g-2 experiment, which gave its final results. But the precursor to this took place in the Brookhaven National Laboratory, and one went under the name of E821, and it finished its analysis towards the end of the last century, and its final results were given in the beginning of the early 20th century. So this had a fair amount of uncertainty. Well, actually it was already a pretty precise experiment, but the goal of this Fermilab experiment was to reduce the uncertainty by a factor of 4. So this is the plan of the experiment. What happens is that protons, and this was at Brookhaven, so AGS is the alternating gradient synchrotron in Brookhaven. There's something different in Fermilab, which hits a target. And in this collision, a large number of pions are produced, which are somewhat heavier than the muon. And these then decay into muons, which are already polarized. They are almost completely polarized. So these muons are all gathered and then collimated and then put inside this ring, and then they go round and round over here in this ring. If the gyromagnetic ratio of the muon was exactly equal to 2, as this went round and round, then this is the magnetization or the polarization vector over here, represented by this cone. These two would always be locked to each other, and then they would just go round and round, and two of them would be locked to each other. But because of the deviation from the value of 2, what happens is that even though they may start out together, as time goes by, because the two frequencies are different, it starts precessing with respect to the direction of the motion of the muon. And that is what is sensitive to the anomalous magnetic moment. So what is the detection principle? So a muon that is going round and round over here, when it decays, it produces an electron and 2 neutrinos, and the 2 neutrinos disappear. And the electron, which will not carry the entire energy, will no longer be able to stay in the beam, and its energy is less than the energy of the muon, and therefore it curls inside into the ring. Simple physics principle, that a particle that is going round and round, when it decays, because its energy is degraded, it will now go inside the region that is of this ring over here. So the detection principle is very simple. You put calorimeters over here and timing information to see when a muon that has detected, when that positron will reach the detector. So that is the principle of this experiment, and the fact that the anomalous magnetic moment has a frequency that is different from the cyclotron frequency. So what is the origin of this discrepancy from the value of 2? So that is the question that we are after, and that is the measurement that this experiment is supposed to have done. It is supposed to have probed the structure of the vacuum. What are all the particles that are present in the vacuum that pop in and out of the vacuum? So the earliest theory in which this was computed was in quantum electrodynamics, which all of you know. It was formulated nearly a century ago by Paul Dirac. Many others contributed to the subject, such as Pauli, Jordan, Feynman, Schwinger, and Tomonaga. And it's the simplest possible theory that you can write down in nature. It has only 2 parameters: quantum electrodynamics. It's a theory of electrons and photons, nothing else. It has only 2 parameters, which is the mass of the electron, and alpha, which is e squared by 4 pi, which is also known as the Sommerfeld fine structure constant. Today we have extended quantum electrodynamics to contain all the other charged leptons, including the muon itself, the tau lepton, charged quarks, etc., etc. And as mentioned before, the free electron satisfies the Dirac equation and predicts the gyromagnetic ratio to be equal to 2. Now, Feynman rules are those that were discovered by Feynman to compute the effect of quantum field theoretic phenomena in the vacuum or elsewhere. In fact, at one loop order, there are only 3 very simple diagrams in this, which go under the names of vacuum polarization, self-energy, and the vertex correction. And it's this vertex correction which gives you the leading order correction to what we call g-2, denoted by a mu. And this was first computed by Julian Schwinger. This was an era when papers were just 2 columns in the columns of physical review or physical review letters. So here you see Julian Schwinger, and here is the answer that he gives over here. This is the number where I have this green laser point, and gives the number 0.00116. Okay, and this formula was checked first for the electron at leading order. It doesn't matter whether it's a g-2 of the electron or of the muon. Both of them give you the same answer. And yeah, that was the whole paper. That's right, the Nobel Prize paper for Schwinger. And this is the Nobel Prize paper for Polycarp Kupsch, who did the measurement of the magnetic moment of the electron. He did it in atomic systems. So Kupsch shared the Nobel Prize with Willis Lamb, famous Lamb shift. So that was jointly awarded to the two of them. And you can see that they also have measured it already using atomic physics systems over here, 0.00116. So that's the number that you have to look at. This particular result, alpha by 2 pi, which is e squared by 4 pi divided by 2 pi, which is the g-2, is so important that it has ended up on the headstone of Julian Schwinger's tomb. And here it is alpha by 2 pi, just as, you know, on Boltzmann's gravestone also his famous formula is present. So the trick is to find some effect named after yourself, which is only a few ASCII characters, so that they can be included on your gravestone also. Yeah. So as I said, at one loop, this is finite, and this is very important, and any one of you can do this in Mathematica. Leo here knows how to do it. If you have any questions, you ask him how to write the Mathematica program, and then it gives the number 0.00116. Okay? And this is all a reflection of the fact that the Heisenberg uncertainty principle for energy and time is something that is written like this, which changes what we call classical predictions into quantum mechanical predictions. But this was only at leading order. We can keep doing these Feynman diagrams at higher and higher loops, and they'll keep making contributions, which will be numerically smaller and smaller, but it depends on your experimental precision. The order to which you want to reach some measurement has to be comparable to what you do as far as the calculation is concerned. Okay? And today some of these things are computed on the computer, and this is called QCD on the lattice, and this actually gives you essentially what we call the standard model prediction for this quantity, which is to be compared with the experimental number that we have over here. This is a depiction of what lattice QCD is. So these are the interactions of quarks and gluons and so on, which also enter this particular diagram that I had shown you much earlier. This particular diagram here actually requires you to compute this, where this blob over here contains quarks, gluons, all kinds of junk that the vacuum may have is sitting over here, which has to be computed reliably. Since you can't do that from, you know, first principles on paper and pencil, you can only do it on the computer. Okay? So that is what is known as lattice QCD, on which these contributions are today computed. So turning now to the results of the experiment that were announced last Tuesday. So this is the muon g-2 experiment 2025 over here. And these, I'm sorry that this thing is almost invisible, but you can get an idea as to the original Brookhaven number was something like this, starting here and ending here, the central value being over here. At the end of the first run, they had a result like this with fairly large uncertainties, but confirming the Brookhaven result. Further data that were collected by the various experiments gave numbers over here, and this is the final answer, and it's an average of all these runs as well as a Brookhaven, which is dominated by Fermilab. Very small numbers over here. And this over here is a number of events collected by the Fermilab experiment, starting run 1, run 2, run 3, run 4, run 5, run 6. So you can see that they have collected a large number of events, and Leo tells me that the number of muons that were collected in this experiment are 300 billion muon events. These are all staggering numbers if you think of that. How is it possible to produce such a large number of muons and isolate them and contain them in this particular circular ring and to do experiments with them? Now this is to be compared with the theoretical predictions like so. So again, we have to go back to this figure over here that I go back to again and again. So this particular diagram that we have over here cannot be computed from first principles. What you can do on the other hand is to use what we call the optical theorem in quantum mechanics, is to slice this diagram into two and think of this as contributions coming from a photon producing pi plus pi minus pairs and then going back into the vacuum. Okay? So this pi plus pi minus, which is produced in various experiments, is used in order to evaluate this particular contribution. So that is what is known as a hadronic vacuum polarization contributions to the muon G-2. And that is where a lot of the problems of the last 20 years have been. How reliable are the hadronic vacuum polarization contributions to the G-2? That's where the controversies are. That's where the experimental and theoretical research and analysis is basically sitting. It's very warm over here. Is the AC on? Yeah. Maybe the subject is heating up. That's probably why we are feeling it. So here is a bunch of experiments from various experiments from a large number of laboratories stretching over half a century. Various experiments have gathered data over here. Here is Chloe, which is an experiment from Frascati in Italy, which is an E plus E minus machine. Then there is Babar, which is a Stanford experiment, again E plus E minus. Here is CMD. This is an experiment from Novosibirsk in Russia. And then this is also another Russian experiment. And then there is also experiments from Japan, Bell. We have a member of the Bell collaboration over here. What happened was that there was a new Russian experiment, CMD3. So as you can see, the theoretical all the theoretical hadronic vacuum polarization experiments are giving numbers clustered over here, whereas the experimental numbers are clustered over here. It's obvious even to the naked eye that there's a mismatch between what theory is giving and what experiment is giving. So when New York Times says that there's a theory problem between the theory and the experiment, this is what they're talking about, that the theory is clustering over here, whereas the experiment is clustering over here. Unfortunately, or should I say fortunately or inexplicably, another Russian experiment produced data all alone contradicting its own experiment. Here is CMD2, CMD3. It produces a number over here, which is in agreement with the experimental measurement. So that's the reason why some of the headlines are saying that there's no real discrepancy anymore. Now, this is going to take many years to sort out, and the theory initiative actually refused to kind of harmonize these two results and instead gave this other green line over here, which is the results from lattice. Okay? Now, lattice is a technique that is used to evaluate these contributions numerically on the computer, and there is also controversy over here. So this is the situation. This is the experimental findings over here, and this is the theory. And yeah, they are all E plus E minus experiments. Yes, exactly. Yeah. Yes, exactly. Yeah. So this was the situation at the end of run 1, which was 4 years ago. So at that time, the lattice did not have any results. So the standard model or this hadronic vacuum polarization was giving an answer over here. At that time, the Brookhaven and the Fermilab results looked like this. This was the so-called 4.2 sigma deviation between theory and experiment. Okay, so then it's a bit of a worry. Why is it that these things are not agreeing? They are still not agreeing, but we have to live with this, and we have no idea why that is. So the theory people themselves have reanalyzed that data again and again, and they did many different analyses, but each one of these experiments and the analysis finds that the answer is quite stable. So each one of them has done it using 3 different techniques, which Leo will mention, but all of them are kind of mutually and self-consistent over there, whereas the lattice is sitting over here. So 1 week prior to this experimental number, the theory initiative, which is again over 100 scientists from all over the world who analyze the data and sit together in conferences and write, they've written a 188-page paper analyzing various different pieces of information. And then this is the message that they have, that they still have this problem, that this is what their theory is giving, this is what the lattice is giving. Finally, they cite only the lattice number as the theory number, which is now in accordance with the experimental finding. So, the summary of these measurements is that, and this is really pretty impressive, this is really the money plot of the stock, is to understand the level of precision at which these experiments are carried out. And in fact, the Fermilab page itself says, the Fermilab is in some place in the US, which also has wild buffalo, bison, so which weighs probably more than a ton. So they said that this is the accuracy of finding whether a bison has eaten a sunflower seed or not. Okay, so that's the analogy that they give for the level of precision that has been achieved by this particular experiment. So, especially our students should pay attention to this kind of numbers where, today we have a measurement of this thing at the level of 124 parts per billion. Parts per billion. Earlier, what was parts per million or parts per thousand have now become 124 parts per billion. This is really a pretty amazing kind of discovery, which is, or a measurement, which is the reason why we are giving this talk. So here's a large bunch of references for those of you students who want to read and, update yourselves on what is known over here. Let me give you a sample of what some of the diagrams look like and what is the kind of effort that goes into actually getting this kind of experimental precision. Now, I've talked about this hadronic vacuum polarization numbers, which dominates the uncertainty. There are large parts of these theoretical calculation which are actually pretty definite, and they actually dominate the theoretical numbers. Okay, and this comes from well-known sectors of the theory, electroweak, like this, where you have something like the Z boson, the various hadronic particles of this kind, and QED. So here is a sample of some QED diagrams. There are literally millions of diagrams which have to be evaluated. So these are Feynman diagrams where Feynman gives you the rules for writing down each one of these diagrams, and associated with every single diagram is a number that you get essentially from the computer, because at this level you can't compute them with pieces of paper. Schwinger could do it at the one loop level. He got alpha by 2 pi by just working it out on paper. But when you have millions of diagrams like this, evidently this is impossible. There are dedicated computer programs, computer algebra, which take months and months of CPU time on supercomputers in order to evaluate them. And look at the complicated diagrams. There are all kinds of diagrams. Some of them, for lack of imagination, are called rainbow diagrams like this, where there are all kinds of incredible diagrams like this with all kinds of complicated topologies. Some of them are planar diagrams, others are non-planar diagrams, etc., etc. Let me say a few words about the experiment itself. It first took place in Brookhaven over here. Yes, yeah. No, that is for the beta function. This, I think it's at 4 loops it's evaluated, but I'm not sure. It's there in that theory initiative, it is covered. The original experiment was in Brookhaven, which is north of New York City, and it was the same magnet which was transported to Fermilab, which is over here. So one would imagine that one could go from here to here, but that's not what they did. They unscrewed the magnet and they put it on a boat, and then they took it down over here, in the Atlantic, what today Trump wants to call the Gulf of America, but the world calls the Gulf of Mexico, and then it goes up the Mississippi River, and then it was transported by road. This is another incredible feat of, transportation and engineering. And this is what the experiment looks like. This is the ring over here, and these are all the detectors sitting over here. And I think the diameter of this is 50 meters, if I'm not mistaken. The 50 meters, I've now got confused between all these. So I'm going to leave it as an exercise for the reader to go and figure out exactly what are the dimensions. But I must say it is pretty big, okay? So this storage ring over here has muons which circulate at this, what is called a magic energy. This is the principle of the experiment. Each one of these is a very beautiful basic physics experiment, which I actually love very much. These two, are they in my slide or it's on this? Huh? On Zoom. Okay, so somebody agrees with these numbers. Okay. Yeah. So I'm glad to hear that. So this kind of precession frequency, now in this particular thing you have a magnetic field that comes out of the plane. The ring is on the XY plane, and there's a uniform magnetic field coming out in the Z direction. And there are various electric fields that are used to focus the beam. Okay. So this particular frequency of the precession is something that is related both to the B field as well as to the presence of the electric field, because there's a complicated interaction given by basic principles from your Jackson or Griffiths. Any such basic textbook will give you the actual motion, the equations of motion, and this precession frequency. Now I had mentioned something called the magic energy, which is an amazing thing. So if you look at the interaction between the fields over here, there's a contribution that's coming from over here, which involves the g-2 of the muon itself. So in order to cut off, to get rid of this interaction, this gamma is chosen in such a way so that this thing becomes equal to 0. And this is what showed up in the standard model exam. How to compute this number 29 is to just use this particular formula, and that was to cancel this particular term. And this corresponds to a muon energy of 3.1 GeV, which is a highly relativistic energy if you keep in mind that the mass of the muon is 0.1 in these units, 0.105 in these units. And as I promised, you all know about relativistic time dilatation. Here, the lifetime has increased from 2 to 64 microseconds. Okay? So what the experiment does is, it has a complicated way of finding out when the muon actually decayed and when it reaches the detector, and it also measures the energy of the positron or the electron that has been detected by the calorimeter. And there is something called the wiggle plot from which this thing is actually extracted. It's a very beautiful principle, this idea of this wiggle plot. So once again, let me go back and tell you a little bit. So what is happening is that you have a motion in this direction, and you have this polarization which is precessing in this direction. Okay? So what happens is that and then these muons they decay by producing the electron preferentially in the direction of the polarization. So let me say that the polarization is pointing in this direction, and then the electron is produced preferentially in this direction. Now, if it is in this direction, then it doesn't get the full Lorentz boost because of the motion of this electron. Of the original of the parent muon is in this direction, whereas this thing is decaying in this direction, it doesn't get the full Lorentz boost associated with the motion over here. Okay? So as this thing is precessing around, the additional Lorentz boost is not contributed to the decay particle. So as a result, there is a wiggle in the number of events and the energy that is received over here. And the fact that the muon is decaying through a parity violating interaction is the basis for why we are able to carry out a polarization measurement in the first place. It's again the same thing. Why is the electron preferentially produced in the direction of the polarization? It's because of the parity violation. So it is a combination of all basic principles that allows this measurement to be made here.
So the wiggle plot, the interaction is going.
Yes. That's because of the radiative decay law. Okay? So if there was no such wiggle, and if you did not polarize it, it would just decay with the usual radioactive decay law that we have all studied in 8th standard. Okay? So that's what you see. But there's a modulation of that because of this wiggling of this frequency which is associated with the G-2 of the muon. It's totally amazing principle. Okay? So these are the various principles, and this is what the experiment does in order to carry out its measurement. So this is what Nirmal is talking about. So this is a log plot, as you can imagine. This is n divided by 149.2 nanoseconds. What is this 149.2 nanoseconds? That is the year on this particular ring where this muon goes around. Just like it's 365 days for us, it's 149.2 nanoseconds for that particular muon. Okay? So it has a birthday every 149.2 nanoseconds. Doesn't have to wait for a whole year like I have had to do today. So thank you for wishing me a happy birthday. Yeah, so anyway, so this is a very clever way of plotting this data, and I'd like you to note this. This thing actually wraps around. The end of this is the beginning of this, which goes all the way around. As Nirmal here just said, this is a radioactive law. So obviously, on a log plot, it's going to be a straight line. Okay? So that's what you're seeing here because it's a log plot. The same log plot continues over here and here and here and here. It's a beautiful way of representing the data. It's like, this seismic meters where you have a drum that rolls around and then you see earthquakes and, all this Richter scale and so on and so forth. Okay. So I more or less come to the end of my presentation, and Leo will say many more things. So this is the plot that we have to take away with us. This is how the situation was at the end of run 1. This was the data, and this was the data over here, and this was the hedonic contributions, and then there was this discrepancy, and this is the projected Fermilab accuracy, uncertainty over here, which they have achieved. It's a remarkable thing. People write down a technical design report for an experiment whose results will come out 20 years later, and of course in your TDR you'll make all kinds of claims, but if you actually achieve something like that, it's really remarkable, and I think this Fermilab experiment has done that for a variety of reasons which Leo will tell you pretty soon. Yes. How do I hear his question? Or is he going to type the question? Maybe he's going to type the question. Yeah. Yeah, go ahead. Can you tell us your question? He can type his question, I hope. Yeah. Or maybe, do you read anything? Yeah. I don't think. Yeah. Anyway, maybe I'll finish my question, few words about my talk over here. So I just wanted to flash only about 2 or 3 slides to tell you a little bit about what is the kind of work that we did. Now, this E plus E minus to pi plus pi minus data will give you measurements of cross-section at many discrete energies, okay? But what you actually need is a continuous description in the energy range where you have to evaluate what is the contribution no matter what the energy of the pi plus pi minus pair is. So it has to be known as a function of the energy that is carried by the pi plus pi minus pair, even though you know it only at certain discrete energies, okay? You can say, oh, I'll always join them and draw a line through them, but that is not a very scientific way of doing things. You have to find a stable, parametric, free way of getting these evaluations using techniques of mathematical analysis. There are many techniques from functional analysis that we have used in order to get really reliable results for what these contributions are, and that is based on something known as analysis of the pion form factor, which has to do with the fact that the pions have a structure, okay? They're not point-like particles. And this is again the use of the optical theorem that I had just mentioned, and using principles of complex analysis and Cauchy's theorem and all these things that you learn in your math methods courses, we have computed these contributions in a very reliable way using all these techniques of functional analysis. I'm showing you these slides just if I had had the time to give a far more complicated, far more comprehensive talk. So this is what these cross sections and all look like, and there's a lot of uncertainty associated with this, which is what gave those several different experiments and all those problems associated with that. So in one of the white papers, our work, that is myself, Irinel Caprini and Diganta Das. Irinel is a very senior retired physicist in Romania. Diganta Das is a former postdoc who is now in IIIT Hyderabad, is an expert on these subjects. So our work has also been summarized in this white paper. So this is what I wanted to tell you about, and we have used these methods to compute various contributions to this hadronic. It was a long project that many of us did with many of my former students, and as you know, which I have frequently been saying, the only good student is a former student. So all these are my former students with whom we have done a lot of this work. There are also very interesting techniques from mathematical physics that we have used and improved and analyzed. We also had a prediction for what is known as the electromagnetic charge radius of the pion that was also related to these things. So this is the references to our work, which is also cited in this theory initiative paper. So this is a summary of our work, which is not so important. So for the future, there is another experiment which has been proposed by the Japanese in, I think it is in KEK, it's called the J-Park experiment, which is a completely different principle. It's based on ultra-cold muons. The muons that we talked about so far, we're at 3.1 GeV. Those are very hot muons. This is going to be in the opposite end. They are going to be ultra-cold muons. They are developing techniques to make muons which are produced very cold, to basically trap them and to measure the G-2 essentially as a static property. So let me finish this talk. Prepared time, 35 minutes. So our results over here confirm, the results from Fermilab confirm the Brookhaven results, the run 4, 5, and 6. And they give this astonishing number over here, this to the power of 10 to the power of minus 12. Remember, this 0.00116 was already found by Schwinger. That's the reason why you always see this number. And the uncertainty over here is down by a factor of 4 compared to that of Brookhaven. And still, there are these standard model errors, which are dominated by hadronic vacuum polarization, hadronic light by light scattering. These things haven't gone away yet. It's just that the lattice now has been adopted by the theory initiative as the standard model. And nobody knows why these things are not agreeing with each other. And maybe more high precision experiments are needed for this pi plus pi minus to really understand where we stand with this. Yeah, question is there? Yeah.
Jayant Mursi said the New York Times article, there was no the article says there is no discrepancy anymore, but that seems to be completely wrong.
Yes, so that's the thing. There's no discrepancy when you adopt the lattice. And the theory initiative has also said that it does not have any meaningful way of combining all the old pi plus pi minus data with the new CMD3. They say that it is impossible to average over these different numbers, so they are not going to do it, and it is left for work for the future. So now only the lattice is viewed as the standard model, however with substantial errors. The lattice still has big errors, so it's not in disagreement with the old hadronic vacuum polarization either within those errors, and this is a very important problem for the community to address. I hope that addresses. Does Jayant have anything more to say? Yeah. Okay, so I stop here. Yes, yeah, go ahead.
So does it mean that the E plus E minus, this thing, the people who did the experiment, they are not claiming that it's no longer?
See, these experiments, so they say that these are our results coming from hadronic vacuum polarization from E plus E minus, and they say we do not know why, we don't have any reason to disbelieve our own measurements, and we do not know why CMD3 alone has a number which is agreeing with the lattice, and CMD3 itself doesn't agree with their own older data from CMD2. So this is all work.
On the very left that you showed are all older data. So
Older.
CMD3 was new.
CMD3, which is an upgrade of the old CMD2, which was anyway in agreement with the other E plus E. So
Other things they are not repeating on, right?
there, many of them are closed down, defunct long ago. I mean, these experiments they don't do again and again, but now there's a need. Maybe someone in the community will have to do this. Yeah. We can have more questions after Leo's presentation also. Okay.
So my part of the talk is mostly supposed to be a supplement to Anna's talk, and it's more about the technical details to show you how they were actually able to achieve such a measurement with such a high precision. So I'm going to focus on some things that are different in run 4, 5, and 6 compared to the previous runs at the Fermilab experiment. But one disclaimer, I'm working in a theoretical group, so I don't have that much of an idea about the experiments. I'm trying to do it anyway, and I rushed this a bit, so about some things on the slides I might be as surprised as you are. But to make it up to you, I'm starting with a small cartoon showing you how the muon actually precesses around its in the cyclotron under the influence of a magnetic field. So don't drink and drive, otherwise. Yeah. No, credits go to my wife actually, who was putting this on paper from, because my artistic talent is quite limited. But yeah. All right, so this part will be divided in 2 subparts mainly. The first one is the experimental details on which I want to elaborate a bit more. And the second part is essentially the hadronic vacuum polarization results that Anand already was talking about and the discrepancy with the CMD3 result. Okay. So we already know that the anomalous precession frequency can be represented with such a formula. So we have influences from the electric fields, from the magnetic field, and of course from the momentum of the muon itself. If we want to get rid of these of the electric part, then we choose the so-called magic momentum. Then this whole last part with the electric field will just vanish. Okay, so we don't really need to characterize the electric field in that much detail, at least at first glance. And we can focus on characterizing the magnetic field, because the magnetic field itself will directly influence the precession frequency. Because, well, the last part we just try to get rid of by choosing a smart, like by making a smart momentum choice. So the magnet itself, like this is a cross-section of the magnets that are used in the storage ring. And you already see here that, wait, you already see that there are some NMR probes that are precisely for measuring the magnetic field during the runtime. And the magnetometer system does not only contain these, there are also some movable magnets, and I want to elaborate on this part first. So the magnetometer system consists of 3 main parts, like in the Fermilab experiment. The first part is arguably the most important, a proper calibration method. If you cannot calibrate the other NMR probes, then this measurement will be essentially useless. The second part is exactly these magnets here. These are fixed. They are just built inside the walls of the vacuum chamber, and they can measure the magnetic field during runtime. So whenever there's a muon beam actually inside, they can track the magnetic field, like they can measure it, and then you can use this information to get some tracking information and to measure, essentially, to carry out the measurement. Inside there are 378 of these NMR probes. Later I will mention that there are like 70-something stations of these, but And the last part, the third part, is the movable NMR probes. They are mounted on a trolley system, and that trolley system can be pulled through the vacuum chamber on a cable, essentially, and like it's being pulled out of a garage. Then they take a bit forward, they go all the way backward and go back to the original position. And they do this roughly every 3 to 5 days, but with a much higher precision. And on this trolley there are 17 probes, and because this trolley is placed inside the chamber, they can actually map the field.
Why do they do this to check?
To check for the field, yes. They want to measure the field distribution. But yeah. But first, maybe we should talk about why they actually use NMR. Well, the final verdict is because it's so precise. But if we, for example, want to design such an experiment, we would have to actually think about what method to use. And one thing that all of us know as physicists is, elementary particles and also a nucleus or hadrons have a magnetic moment, so they have a jar magnetic ratio. And the one of the proton, for example, is just very precisely known. So you can measure it very well with a relative uncertainty of about 10 to the minus 10 according to CODATA. So once you know this gamma p value, once you know this jar magnetic ratio, to such a precision, you need to only measure either the precession frequency, like the Larmor precession, or the magnetic field to get the other one. So this is what you actually can use, and this is the basic principle of NMR. So you rotate the spin of the proton of a proton out of the magnetic field, and you let it precess and relax. So you measure this frequency, and then you can conclude what the magnetic field actually was. Why do we use protons, or why might protons be a good choice? Well, the mass of the proton is so large, for example, compared to electrons, that the Larmor precession frequency is low enough to measure it precisely. And it's also not too low in this case compared to the frequency of the muons inside the ring, that this is a good way to measure it. I think, if I'm not mistaken, with a proton mass and a field of about 1 Tesla, you would have order of 100 megahertz of Larmor precession, which is still handleable from an experimental standpoint. Okay, but we cannot just put protons inside a sample holder and measure protons, because that's not going to work, because they're positively charged. They will just you have to actually trap them, or you use a chemical in which there are protons that are very comparable to the free protons in terms of this interaction with the magnetic field. And hydrogen is such a candidate. For example, the proton in hydrogen that is bound in water has a gyromagnetic ratio that is very, very close to the one of a free proton. I mean, this value, it's just an estimate. I just plugged in some values from CODATA and got this. And the advantage is that water itself is very abundant on our planet, and it's easy to purify and also well characterized. So this would make maybe a very good calibration probe. And this is actually what they use. So they actually use a water probe for calibration. And the other probes that are mounted inside the walls of the vacuum chamber and that are mounted on the trolley, they're actually not water-based. They are using a petroleum jelly because petroleum jelly is a very proton-rich sample. There are a lot of hydrogens inside, and this way, and this has actually several advantages. One of them is that you can get a much larger signal out of it, and you just fill it once and it doesn't evaporate, nothing happens with it. So you just put in your petroleum jelly once and then that's it. It just lasts for a very long time. But of course it needs calibration because every sample might be slightly different, but this is exactly where the water-based probe then comes in. The water-based probe itself also must be calibrated, and this is done in two ways. One of them is with a very precise magnetic field at ANL, actually. And the second one is cross-checking against a helium-3 probe. And if I'm not mistaken, this helium-3 probe is actually coming from J Park. But yeah, I'm not entirely sure on this now. Yeah, but so these are essentially the probes that they use on the trolley system and also on the fixed ones. So the fixed magnetometer NMR probes are located at 72 positions around the ring. Each position is called a station, and on each station you either have 4 or 6 of these NMR probes to just track the field in real time during operation of the experiment. And the trolley, I think I said this earlier, is pulled through the ring every 3 to 5 days to actually track the distribution of the magnetic field. This way, I will show a plot later, we can also see how pure the magnetic field actually is inside. And this is done with much more stops throughout the ring. There are more than 8,000 stations at which this is done. Of course, once the trolley is there inside, then you cannot really trust the measurements of the fixed probes again, because the fixed probes themselves will be influenced by the presence of the trolley, like by the material and also, of course, by the electronics inside. So it's you need some procedure to actually veto these measurements. So this is actually what they do. They check where the trolley is, and if you measure close to another probe, then you veto this measurement, you don't take it into account, and you just extrapolate from nearby fixed probes. This way they can decrease some uncertainties in the magnetic field measurements as well. Okay, so in run 1, they took they took 16 magnetic field maps, which means actually cross-sectional maps from the trolley. In run 2 and 3, they increased this to 69 maps, and after run 6, they increased the number to 194 magnetic field maps in total. And of course, if you have a higher number of maps, then you will be able to decrease your uncertainty of the magnetic field measurements as well. In this case, from about 38 parts per billion down to around 30. But all these tiny increments in precision are actually needed if you want to achieve this incredible precision that they achieved now at Fermilab, actually. And yeah, the angular distribution of the magnetic field has variations that are also very low, about 20 or smaller than 20 parts per million, but not as well as it's still like orders of magnitude away from the PPB actually. All right, here you actually see this is a plot from the newest publication where they also presented the results. So what you see here is two things: an overlay of, first of all, the magnetic fields as deviations from the homogeneous value in ppm, and color-coded you have the muon distribution here. So you really see that most of the muon distribution is actually in a very, very homogeneous field where you don't have any variation from the ideal value. But the question now remains, how do you actually measure the muon distribution? Because the magnetic field, okay, we know this, they just take a trolley, they pull it through, they have 17 probes, so they have a local distribution, so that's fine. But how can you actually achieve such a measurement of the muon distribution? Well, this is what you do with the tracking systems. Ananth already told us that there are 24 calorimeters around the ring, like inside the ring. But each calorimeter actually comes also with a tracking system before. So if you have a muon and that muon decays into a positron, and you track that positron, what you can do is you can extrapolate the trajectory to where the muon actually decayed. And you do this... Yeah. Sorry? The muon decays to a positron and neutrinos?
It's mu plus.
Yes. Yeah, exactly, it's mu plus.
They've done the experiment with mu plus.
Yes. Yeah, so you just extrapolate it back to where the muon decayed. You do this for many events, and then you average over time, and you average also spatially, and then you get these kind of plots here these kind of distributions, because you just inferred from where the muons decayed. Okay. Also because they used more magnetic field maps, like 194 magnetic field maps in the newest runs, they were able to decrease the tracking deviation or the tracking uncertainty as well by a factor of 2, like half, roughly. Okay, and
Sorry, this may be jumping ahead a bit. If the net uncertainty is like 120 parts per billion, the tracking uncertainty is only this much, and the magnetic field uncertainty is only 34 parts per billion. What is the biggest uncertainty?
I will show 2 tables that compare run 4, 5, and 6 and run 3 later. Maybe we can talk about that then, because they have all these uncertainties for the corrections of the ratio that they actually measure. So maybe we can postpone it until then. Okay. All right. So yeah, the tracking system itself is a straw tracking detector. That means they are just tubes filled with a gas and with a small wire, and they have a high voltage. So when a charged particle goes through them, they ionize. And you can actually measure this in terms of a current. I think this is very similar compared to what they use at Atlas and CMS as well for the tracking. And the calorimeter itself is a lead fluoride Cherenkov detector, meaning what they actually measure in the calorimeters is Cherenkov radiation, like a pulse of light, same way as we measure the neutrinos in these large Cherenkov detectors at Kamiokande, for example. And the readout happens via silicon photomultipliers and meaning they don't use these high voltages that you use for photomultiplier tubes, which is much better when you want to have get the high voltage inside the vacuum chambers or something like this. Okay, this is a sketch of the calorimeter system together with the tracking detector. So you see here they have several stations, and whenever you measure a signal here, you can just say where the positron was, and this way you can get this path and extrapolate it back to the decay point. Okay, so now we know how to deal with the magnetic field. The magnetic field can be measured quite precisely, but of course there are other uncertainties present as well. One uncertainty also comes from the beam injection itself, because if you inject the beam inside the storage ring, how can you be sure that you only inject muons? Because we know that the muons are actually coming from decaying pions, right? So some of these pions, or maybe even some of the protons that you use to create the pions, might be entering the storage ring as well. So what would happen if that actually takes place, and how to deal with it? That's a very important question to reduce the uncertainty as well. So first of all, of course, there could be some of the beam particles that directly hit the detectors. What then happens is you measure the signal, but you will saturate the electronics. And this results in some kind of effective gain reduction. The capacitors might be depleted, so you don't have that much gain when you want to actually measure your decay products of the muons. And another effect is coming from neutron decay. So if a pion or a proton hits the surrounding materials, like the walls of the storage ring or anything else, they can create neutrons, which can then be captured, and the neutron capture emits gamma rays. And if these also enter your detector, like the silicon photomultiplier, this also results in some kind of overload, or not really an overload, but it's just a saturation of the electronics. Okay, so how can we deal with it? At Fermilab, they thought, well, maybe we can just have a reference signal. We measure that reference signal, and then we can measure gain variations. So this is what they've done. They used a laser for this. They measured that laser signal, and whenever there are short-term or also long-term variations in the gain, they can read this out, and they can use it for a correction. I unfortunately don't know by how much they exactly were able to reduce the uncertainty coming from the hadronic flash this way. Maybe someone of you knows, but I couldn't find any reliable numbers on short notice for this.
I saw a claim that they completely eliminated the hadronic flash at the time of run 1 compared to
I saw a design study. They claimed, or they were hoping for something like a factor of 6 improvement. So because there are some problems, like you might also imprint the actual oscillation that you want to measure into this feedback with a slight phase shift. So I don't know if that because then you have like a feedback that is more difficult to handle. But I don't know how much this actually affects all these measurements. Okay, so another thing is what happens actually, like you take these muons, you inject them, let's say we don't have problems with the hadronic flash, but we still need to handle the beam itself. So we need to handle the beam dynamics. Of course, the magnetic field inside will result in the, that the muons just circle on travel on a circular path. Okay, but how do we prevent that beam from dispersing and from the muons just hitting the walls and being essentially lost in the experiment? Well, in the Fermilab experiment and also in Brookhaven, they used an electrostatic quadrupole system for this, meaning they use an electric quadrupole field to actually focus the beam vertically. The horizontal focus can also be done with this, and also the magnetic field is reliable because, well, the horizontal one means it's essentially the radial direction. Okay. The problem is that just preventing the beam from dispersing is not the only issue. Another issue comes from actually how you inject. So how do you inject? You take the muons that are coming from the pion decays, and you need to put them on the correct path, on the accepted path by this storage ring. And this is done using a so-called kicker magnet, which is supposed to bring all these muons into the ideal orbit. But the kicker magnet, of course, is also not ideal. In fact, they are under-kicking, meaning they don't give enough of this boost to prevent muon loss, I think. And this results in a phase-space mismatch. So suppose, do we have some chalk here? Suppose you have the XY plane, and maybe your storage ring wants to have muons here with the correct momentum. What the kicker essentially does is they slightly displace this. And what then happens is the whole beam itself will undergo some Betatron oscillation. So the whole beam itself will not stay on a perfectly circular path, but will start to oscillate and start to wobble. And the people at Fermilab came up with a very smart way to actually resolve this using already existing systems in this storage ring. So they took the electrostatic quadrupole system and employed like an additional radio frequency modulation on this to counter all these Betatron oscillations that they have to make them to make this oscillation decay much faster. This happens in the order of the first 6 microseconds after injection. The correction they get from this is from 0.8 ppm to down to 0.1 ppm in shift of the measured frequency. So that means they just have to correct less for it. I mean, yeah. Okay, so this RF system that is actually new, that they didn't use this in run 3. So up to run 3, like after run 3 in 4, 5, and 6, they used this in 3 of the 4 data sets. And what this essentially does is that it tries to rebalance the muons. Like the low energy muons are pushed more close to the ideal orbit, and the high energy muons are pushed slightly away, so that you again get an overlap. So you're not in the exact ideal orbit that you want, but at least you have an overlap, and this way you can also reduce the some uncertainties that you have in the muon distribution, like that plot that I showed before with the magnetic field. So this is also being improved by this. And another thing is you get less muon loss because less of the muons hit the walls of your vacuum chamber and are not participating in the experiment anymore. So here you see that in which datasets they actually used this. So until or up to run 3, they didn't use the RF mode at all. And in the new runs, in 3 of the 4 datasets that they analyzed, they used this new technique in 2 different variations, meaning either only horizontally or also horizontally and vertically. All right. Here is, by the way, the plot regarding all these correction factors. This is just a list of all the correction factors that they use to correct the actual measured ratio of the anomalous frequency to the precession of the NMR probes. Because the precession of the NMR probes gives you the magnetic field, so you end up with a ratio of these 2. And the hadronic flash, for example, the RF system, for example, results in a less correction that you need for the electric field influence of the beam dynamics compared to the previous publication. And here they say they have a total uncertainty of 139 parts per billion compared to 215 before, but the main advantage that they have actually comes from the statistics. So the statistics itself, of course, play a very big role. And we saw that they analyzed somewhat about 300 billion positron events during the course of whole Fermilab experiments, up to run 6, or until run 6. Okay, so even though they do correct for the coherent betatron oscillations that they have, they cannot completely get rid of them experimentally. So what they do is they have to model them from a theory point of view and also have to then include them in the fits. So here you see these wiggle plots, right? So the wiggle plots need to be fitted, and from the fit parameters you can then extract the value that you're actually interested in. And if you do not correct for the betatron oscillations that you have, then the Fourier transform of your residual will still have strong peaks at the position of this frequency. This is already reduced due to the RF system. I'm not sure exactly by how much, like what's the numerical value there. But the point is that if you take this and you put in a proper model, like you need more fit parameters, of course, but if you can model these oscillations and then you can get rid of them in the fit and pushing the residual actually to these peaks not being visible anymore. Okay, so of course we now talked a bit about the experimental uncertainties that are there, but this is not the only source of error. A large source of error can always be the person in front of the computer who does the analysis, which is what I labeled as a researcher bias. Maybe the researcher wants to be more close to the standard model, so he doesn't do it consciously, but he might just tweak parameters in a way that he agrees more with the theory or deviates more depending on how much he likes us as theorists. But what Fermilab does is they're doing a blind study, essentially. So there's a blinding procedure that tries to facilitate these issues. And the blinding procedure works as follows. So you want to measure a frequency. So the frequency you measure from these wiggle plots, right? So you need to have a very precise time measurement. You need to have not just one time measurement. Actually, you need to have several connected time measurements coming from the anomalous precession frequency that you measure and also from the NMR probes, and you need to connect them, which is why they use a GPS signal for this. Like they use a GPS, I don't know how this works, like it's some kind of distributed timestamp that they use for both at the same time. But the point is that the exact sampling frequency of the calorimeters are not known to the analysts. So there are, I think, 2 Fermilab scientists outside this collaborations that are choosing or tweaking this clock by about 25 parts per million in either direction, like order of 25 parts per million, but the exact value is not known to the people who do the analysis. And then everyone from these groups just design their analyses, they try to measure all of this, and when they are certain that everything works well, then they reveal this offset in the clock, and the real value can actually be calculated. And it's not just this, they also, like the groups themselves, like among the groups, they don't share the same offset, because every group blinds with the software offset again to not do the same mistakes, essentially. Okay, so here you see this is the whole timeline. I think Anand showed this plot already. And at the end of run 6, they analyzed about 300 billion of positron events, which is again a factor of 3 more compared to, or more than a factor of 3 more compared to the end of run 3, actually, which is an incredible amount of events that they had to analyze. Okay, so this brings me to the end of the experimental part, and now I want to say a few words about the discrepancy of the final result with the theory. I'm not a QCD expert, so I hope I get this correctly. So if someone of you is an expert on this, please speak up. The first point is, we saw this plot already, but why are there exactly 3 lines, like 3 reported values per experiment? And I tried to find out about this over the weekend, and as far as I understand it, it is that there were 3 main groups coming up with how to do the experimental analysis, meaning how to actually get the anomalous magnetic moment from the collider data that they gather. Here's again another plot which is maybe a bit more visible. It's not the same thing actually. It's here they only look at the pion contribution, but here it's just a bit more zoomed in. Yeah, and you also see the large deviation of the CMD3 experiment there. Yeah, okay, but coming back to the QCD parts.
The previous one, those are different sets of authors.
Yes.
Each one of those.
Yes, each one of these corresponds to the initials of the authors of the groups. And each of them comes up with a different analysis for essentially this value here, which is directly connected via the optical theorem and analyticity and unitarity to the hadronic R ratio, or to the cross-section of E plus E minus two hadrons and a photon. And for example, the people here labeled KNTW, I unfortunately don't know their full names right now. Just to tell you how it looks like, these people come up with an analysis that tells you that depending on root S, the total R ratio is to be composed of the sub-processes in exactly this particular way. Looks very complicated, it is very complicated. I could not understand how this actually works in on such short notice. But yeah, you need to just remember that there are 3 of them, and these 3 analysis types are exactly what corresponds to these lines.
So the authors of the CMD3 are also the same set, is it? So in the previous
So CMD3 itself is an experiment.
No, I understand, but in the author list, in the triangle, etc., you said was...
Where?
No.
Can you just
Those
go
are
to
theorists who have...
Previous? This one?
No, the one with the... Yeah, this one.
Yeah.
So there, the triangle and this thing, so those are up there, they are different. That's what you're saying.
So I'm just saying that for the triangle, for this symbol and for the square, there are 3 different analysis types, and the people who came up with this are labeled by this.
So the groups are different, but the methods are what the labels are.
The experiments provide only the cross-sections.
Yes.
How to interpret that cross-section and to translate it into the hadronic vacuum polarization is done by theorists. 3 different groups of theorists, each composed of 5 authors or so, to do each of these analysis from the raw data supplied by all these experiments.
The optical theory.
Yeah.
Yes. And also for those, there are many final states. In the next slide you showed there are all
Yes.
kinds of final states. So how to account for them, and then there's some model dependence and so on.
Yeah, so essentially for example, the CMD3 or whatever experiment just gives you some numbers for the cross-sections of E plus E minus to pi plus pi minus, for example.
Can you just go back one more to the one before? I think the one.
This?
So here, for instance, the idea is that you get the raw data, but then the translator is basically the triangle, this thing.
Yeah.
Yes.
And the triangle is a method, basically. And that's somehow a standard method, but it's somehow the data is what is much more.
Yes. The data are different from, but the curious thing is if you look at CMD2 and CMD3,
Yeah, they are quite far apart.
Yeah.
What is the gray band?
the gray band is
The average, I think. So the theoretical uncertainties are here, but if you average them, that should be the gray band, I think. Yeah.
So this is only E plus E minus pi plus pi minus or any hadron?
Yeah, this is specifically for a dispersive analysis that mainly uses the pi plus and pi minus.
It's completely dominated by pi plus
Yes.
pi
But there
minus.
should be other subdominant contributions.
I think that's what is in the
Yeah.
other picture, right? Wasn't that?
Here, this one, yes. This is the full picture, yes. Like in the KNTW analysis, this is exactly how all the other final states are being combined to give the full R ratio.
This one is in the ratio hadron production divided by...
Yes, so the full R ratio is this color here, and the other ones on this log scale just show you what fraction is which final state compared to the energy. Like where these exactly come from, I also don't understand. But people who are a lot smarter than me, they thought about this for many years. So if anyone has experience with this, maybe it's probably better if that person answers compared to me.
Oh, we can invite one of them to give a talk, also, online talk.
Okay,
We can
yeah.
also pay them airfare to come in.
Then I can ask them all these questions. Okay. All right. So yeah, this is just to give like an interpretation what these 3 lines per experiment actually mean. And now of course, the discrepancy of CMD3 to the other ones are still there. And I don't exactly know why the discrepancy is there. After this result was published, there was also a special conference on this. And the result of this was a paper with 41 questions to them. So many people had questions why this discrepancy is actually there. But some things that are different from the other experiments is that this is a more new result. And compared to the previous one, the CMD2 version, they got a full detector overhaul. For example, they have a new drift chamber, they have new calorimeters, they have new electronics. So this, of course, might be, one reason might be that the experiment is just much more modern than some of the others. But
What about energy? Like CMD2, CMD3, they have the same energy range or?
I'm not sure they are at the same collider as the SND6, I think, in Novosibirsk. I think both experiments are there, but
energy scan. But
they have a scan.
They probe the low region and lower energies also. I don't know exactly.
Yes,
They don't go very close to threshold, but
they also need to have a scan because they want to evaluate this integral. Yeah.
So all of the CMDs are some Russian experiment, correct?
Yes. So they are in Novosibirsk at one circular collider. And another experiment that's at the same collider is this SND experiments, actually.
yeah, Babar is American, Stanford, Chloe is Italian and Frascati, West 3 is Beijing, and the others are Russian experiments.
Yeah. So this is also important because this SND20 and CMD3 are at the same collider. So it's probably an experiment thing and not a collider thing. This discrepancy that's there also between these two.
And also this CMD3 was like, is there a time difference between when these experiments were done?
Yes.
I think these ones are older ones, right?
Yeah, all the upper ones are older than CMD3.
What about SND20?
I don't know when they published their results.
I think that's a year, 2006 and 2019.
Maybe.
Yeah, that's right, yeah.
Yeah.
So one more question. There should be something from male too also, right?
So it's
At
not,
higher energies.
it's not
No,
always
power is there. Power is also very deep.
No, but the Bell data is at higher energies.
So Bell 2 is working on it.
Yeah.
Because
Bell,
power and
Power and Bell 7 and
Same.
City. I
Yeah,
mean,
there's no
7%.
result. We've not published anything in this region.
Bell will work. Bell 2 is working on it.
Yes. Yeah. I guess even generally is
Yes,
part of
that's
the
what I
analysis.
meant.
He is leading.
Yes.
Yeah. So please tell us what the answer is. No Nobel Prize, we'll keep praising.
Okay. Yeah, but the
So what is EE there? Is it E plus E minus 2 pi pi or it's something else?
you mean
In the x-axis, pi pi E.
yes? This is E plus E minus 2 pi's. Yes.
So all these are E plus E minus pi.
Yes, all of them are E plus E minus colliders as far as I know.
You asked a very important and interesting question because the tau decay, the tau also decays into a rho and so on, also produces, and that result from there, which is not being used in this analysis, is closer to the lattice, but there are issues with the extraction because the tau decay has important issues associated with isospin breaking, which theoretically nobody has sorted out.
I'm not sure.
Because the data is there, now somebody has to do the theory to do it.
Yeah, I think in the final theory report this is also included.
Yes.
Yeah.
Tau. you see,
Yes.
it's tau decay.
Okay, yeah, so the CMD3 result did get a full detector overhaul with electronics and everything, but still there are some things that are not really well understood. For example, they, in the final publication, give one systematic uncertainty, but some of the analysis that are being done need intercorrelations between some of the processes that are not really well understood then, or at least people don't really know if the analyses that are being done on this are then actually with the reported uncertainty, or if this is maybe larger. So the point is to take CMD3 with a grain of salt until this has been sorted out. And yeah, this is everything I wanted to talk about as a kind of supplement to the general talk that Anand
That
gave.
was a supplement to your talk.
And yeah. All right. Any questions?
Predictive is probably working on E plus E minus 2 pi 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 G.
That might be, but again, I'm from a theoretical group. I don't know about all these experimental collaborations. Okay.
How are these theories who are using these experimental data, are they looking at the, how to say, match the data?
Yeah, this is the point. So the point is of this whole theory group is, I mean, there was this update on the Muon G-2 theory just recently. This 188 pages theory paper. The whole purpose is to give a precise prediction and to get rid of all the uncertainties in the theory part, to actually make precise if there is a discrepancy between theory and experiment or not. So this is exactly what they want to do.
Yeah.
Sorry?
But lattice has large errors. Yes, but it agrees. It has been agreeing since the run-to time already.
So yeah, when people say that that there either is an uncertainty or not, this mainly means if they believe lattice or CMD3. Yeah?
Okay, so this might be very reductive, but I'm always nervous about the fact that both experiments use the same storage.
Yes. This is why J-Park is so important, because if there are some, I mean, these groups do their best to eliminate all these things. They try to make modifications to the IISc system. They try to make modifications to almost everything, but still it's the same storage ring. So if there's an uncertain, like a systematic uncertainty there, yes, exactly. But this is where J-Park comes in, because they have a completely different way of measuring this. So that's it's a Japanese experiment in the future.
And a different continent.
Not with the storage ring.
And not with
Yeah.
Earthquakes also.
Right.
That can change the frequency of the muon.
Right. Any other questions, or to the previous part?
I think we have just enough time before the next talk begins.
Good.
In 10 minutes.
Right.